Okay, hello everybody. So, in this series of lectures or in this module, we will essentially revisit what we had learned in our basic signals and systems course. So, in order to make this course a little self-contained, we will quickly run through those concepts, especially of Laplace transforms and the several properties associated to it. We will take a slight detour because at the moment we will not do linearization of nonlinear systems. We will do that slightly later when we will deal with state space, right. So, starting with basic definition of signals or basic classification of signals, what we would learn in basic systems course would be to essentially differentiate between time domain and frequency domain. Okay. So, what does the time domain do? The time domain shows how a signal changes over time. Similarly, the frequency domain graph shows how much of the signal you have within each frequency. For example, even when you do things like filters like low pass, high pass, band pass and all pass filters and so on. Okay. So, in time domain, the magnitude of the graph as each instant is represented. When you draw a graph, I will show you examples of this very briefly when we do this, when we learn of what this actually mean. Similarly, in the frequency domain, the signal is represented by sum of sinusoids of different frequencies with certain magnitude and also in some cases a certain amount of phase shift. Okay. So, what do this mean? So, let us take a very simple looking signal x of t, which is a composition or addition of two signals sin t plus pi over 3 plus 2 sin 2 t. Okay. So, at t equal to 0, if I compute the value, so this guy goes to 0, I am looking at sin pi over 3 and I get a certain value. Okay. At t equal to pi over 6, the value becomes 2.7, at t equal to pi over 2 and so on, and I can get this nice beautiful looking graph over here, right. Okay. So, what happens in the frequency domain? Again, so here the signal is again composed of two signals sin t plus pi over 3, the graph of it looks like this, and sin 2 t looks like this. So, typically a signal when we represent, we write it, or at least a sinusoidal signal, as a sin omega t plus phi, okay, with the amplitude, the frequency and what we also call as the phase shift, right. So, here if you take these two signals t plus pi over 3 and 2 sin 2 t, well, they have two frequency components. Okay. What do I mean? Now, look at the signal sin t plus pi over 3, and if I compare with this expression over here, so here the amplitude is 1, right. So, if I denote the amplitude as x, the amplitude would be 1, omega would be 1 and the frequency would in turn be 1 over 2 pi, or the time period is 2 pi, therefore, the frequency is 1 over 2 pi, and phi, the phase shift would be pi over 3, right. So, this signal has omega as 1, frequency as 1 over 2 pi, magnitude as 1, phi as pi over 3. Now, look at the second signal 2 sin 2 t. 2 sin 2 t has, so this is with a 2 here, so omega would be 2, frequency would therefore be 1 over pi, or even its time period if you look at, so this has twice the time period as this guy, the magnitude is 2 and there is no phase shift. Okay. Now, if I were to represent this two frequency components in a graph, I look at the amplitude plot, right. So, this signal, the first one sin t plus pi over 3, right, exists only at a frequency of 1 over 2 pi, at frequency of 1 over 2 pi and with a magnitude of 1, right. So, this is its frequency. So, this is its frequency and the magnitude. Okay. So, and look at the second signal 2 sin 2 t, which exists at a frequency of 1 over pi with a magnitude of 2. In the graph it could be represented 1 over pi and a magnitude of 2. Okay. Now, what about the phase plot? Well, the first signal sin t plus pi over 3 has a phase shift of pi over 3, right. So, this is corresponding to frequency 1 over 2 pi, I have a phase shift of pi over 3, and this guy does not have any phase shift. So, at 1 over pi I just have a 0, right. So, this is the frequency domain representation of these two signals which are represented in time domain as a sin t plus pi over 3 plus 2 sin 2t. Okay. So, more on this will come later, but this is just a nice explanation of what is happening in the transition between time and frequency domain. Okay. So, given function or a signal, what we see here is we can actually switch between the time and the frequency domain, and this can be easily done using some kind of a mathematical transform, right. And what is a transform? Well, Fourier already told us that any signal in the time domain can be represented as summation of sinusoids of different frequencies. We have this infinite series and what we call as the Fourier series, and also resulting in the Fourier transform. Okay. And why are sinusoids so useful to us, right? So, if I take a system which is LTI, which means linear time invariant system, and as the input I give some sine wave, right, and then the output would be some sine wave, maybe of different magnitude, right, and some phase shift. So, sinusoids are preferred because they do not change shape when passed through an LTI system. There can only be an amplitude gain and a phase shift. Okay. Everything else remains the same. On the other hand, if I send a square wave, right, the output will not be a square wave. Okay. And therefore, analyzing sinusoids is important or is useful, because if I send a sine wave, I will still have a sine wave over here. Only thing is, if this is sine omega t with a magnitude a, this guy could be with some other magnitude sine omega t plus some phi. Okay. That depends on what is sitting inside here, right. This a bar phi depends on what is sitting inside this LTI system, but the frequency remains the same, right. This does not change. Okay. And of course, I could analyze these signals based on the Fourier series, that that any signal can be represented as summation of sinusoids, and therefore, I could even analyze these kind of signals by making use of this transformation, that a sine wave here transforms very beautifully to this side. Okay. So, are there any advantages or disadvantages of writing things in the time or the frequency domain? Well, each domain has or provides us with its own information, right. It depends on the objective, what kind of information we are looking for in the system. So, an analysis done in one domain could be in sometimes advantageous over analysis in other domain, and that we will investigate slowly as the course progresses, right. For example, a signal having characteristics that change with frequency can be easily analyzed in frequency domain compared to the time domain, right. So, here in this signal, in this things, if you see, so here the frequency domain is more or less not very informative, right. Whereas there is some kind of different things happening as the signal progresses over time, right. So, possibly here, maybe again depending on the objective, we could either use the time domain or the frequency domain analysis. Okay. So, what is the relation between what we have learned earlier and then what we are trying to do now, right. So, we all know, or we discussed this extensively, of modeling a mass spring damper system or a second order system with mx double dot plus bx plus kx equal to 0, and if I aim to solve this equation, it would have a e power minus sigma t term and some sinusoidal term, right. It is maybe a first course on differential equations will tell you this, and this number sigma, a, omega, phi will depend on these parameters m, b and k. Okay. So, we are not at the moment not interested in what is exactly the sigma, what is exactly the a or the omega or the phi, just we are interested in the form of the solution, and the form of the solution has an exponent term which is, well, possibly decaying, in this case it is decaying, and then a sinusoidal term, right. So, the solution to the equations has an exponential term and a sinusoidal term. The exponential term is usually because of the damping term here. Okay. So, if b goes to 0, then I will have a system which is mx double dot plus kx equal to 0, which we know has a solution of the form a sin omega t, possibly with a phase shift or not, right. So, it will just be, so the solutions will just look like periodic ones, right, these ones, right. And this has a nice physical interpretation also, right, that if there is no damping in the system, then my system will just keep on oscillating and the energy will keep transforming just between the mass element and the spring element here. Okay. And this, once I have B, I have some kind of a exponentially decaying term, which the response would then look like something like this, right, that the response will eventually go to 0. We will do this analysis a little later, right. So, the exponential term is due to the damper, whereas the sinusoidal term is due to the interconnection between the mass and the spring. If there is no B, they will just keep on exchanging energy. If there is a B, the energy will exponentially decay to 0. Right. So, this is how they look like, right. So, sin of t is just a nice periodic signal for all times t. E of minus 2t, for example, just goes down to 0 exponentially, and a combination of these two signals, e power minus 2t sin t, it just looks something like this, right. These are also called as damped oscillations. Okay. Okay. So far what we have observed is that solutions could have a combination of exponential terms and sinusoidal terms, or either just an exponential term or also only a sinusoidal term, as we saw in this thing over here. Okay. So, in the frequency domain transformation, the signals are decomposed into sinusoids, which are described by again an amplitude and phase at each frequency, as we saw in the earlier examples. And in addition to this, now what we have to do is also to account for, instead of just sin omega t plus phi, possibly with a magnitude a, we also have to account for the exponential response, which was e power minus sigma t in the previous slide, right. So, can we combine these two into a single idea or a single transformation that will help us analyze the systems better, right. So, what we need is a new transformation such that signals are decomposed into both sinusoids and exponentials. Why? Because our solutions essentially consisted of these two components, right, the exponential component and some terms which were just sinusoids. Okay. And that is where the Laplace transform comes into picture. What does the Laplace transform do? The transform decomposes signals in time domain into a domain of both sine and exponential functions. So, here sine is not only sine, but it could also include cosine terms and so on. Okay. So, this domain is called the S domain or the Laplacian domain, and invented by Simon Laplace, and I think the name S, the S comes from Simon. Okay. So, S is essentially a complex number, right. S is usually sigma plus j omega that we learn in our basic signals course, is 2 dimensional. The first dimension, this corresponds to the frequency of the sinusoidal component, and second describes the exponent. So, if I just write down the signal of this form e power, or a component of this form e power st, so S is decomposed into the exponential term and the sinusoidal term, and this expands as e power sigma t cos omega t plus j sin omega t. Okay. So, by definition, how do we find the Laplace transform? So, given a signal x of t, right, the Laplace transform is given by L x of t, I call it as x of s because I go from the t domain to the s domain, usually computed as 0 to infinity x of t e power minus st dt. In most texts, you would see this as 0 minus. That would account to the question of what if there is an impulse at the origin or at when t equal to 0, right. We just start just at t minus, but for all purposes we will stick to the notion of notation of just having a 0 here, right. And this L is the Laplace transform operator, which transforms a signal from the time domain to the Laplacian domain via this expression. Okay. So, now the question would come, well, can I always solve this integral? Does the Laplace transform always exist? So, we will try to answer those questions. So, existence depends on the convergence of the integral. Does this integral exist, right? And in the region in the s plane for which this integral exists is called the region of convergence. Okay, we will see these things through help of some examples. Okay. So, let us take the very basic of signals, the impulse function, right. And I say Well, find me the Laplace transform of just the impulse function, right. So, which is usually denoted by delta of t, and I just use the definition here 0 to t x t e power minus s t dt, replacing x with delta, I am left with this expression. Okay. Now, I can just compute x of s to be 1, where I just use the property of the impulse function, where the impulse is defined as 0 to infinity delta t is 1, right. And again, most of the analysis here we will do is again from 0, even though there exists something called the bilateral Laplace transform, which actually go from even the 0 replaced by minus infinity. Okay. But since throughout this course we are interested only in causal signals or causal systems, we restrict our analysis to just this one, right, things starting from 0. Okay. So, making use of this property, that 0 to infinity, or even say this could also go from minus infinity to plus infinity, that delta t equal to 1, I have x of s equal to 1. So, the Laplace transform of an impulse signal is just 1. Okay. Now, let us take an exponential signal, Laplace transform of e power minus a t. I substitute into the definition of x of t here is e power a t minus s t dt, and I use the basic formulae for integration, and what I see is x of s, where x of t is e power a t, the Laplace transform is given by 1 over s plus a. Okay. Now, is this enough? Does this exist all the time? Well, now let us take the case here where, now here I am just evaluating these things, right, e power minus s plus a times t, right, and I say, well, do this from 0 to infinity. Okay. Now, what happens if this guy is positive, right. So, if s plus a is less than 0, then I will just have a term e power some number which is a positive number here times t. Okay. And this, as t goes to infinity, does not exist, right, it also goes to infinity. Therefore, all these things, or the Laplace transform of L of e power minus a t equal to 1 over s plus a, exists only in this region where s plus a equal to 0, right. So, if I just draw it on the s plane, split as sigma and j omega, right. So, the real part, that sigma, if I put this here, I call this minus a. So, this guy will only exist for these regions, right, for which sigma is greater than minus a. For all other sigmas, this limit here will not exist, because I will have something like, loosely speaking, e raised to infinity. Okay. And I want to avoid those things, and that is the notion of region of convergence which we had talked about in the earlier slide, right. The region in the S plane where the Laplace transform exists is called the region of convergence, and this is precisely the reason why we need to define the region of convergence, right, just because of this one and this one. Okay. So, let us quickly run through just computing Laplace transforms of few very basic signals. If x of t equal to t, I can compute this just by standard integration by parts, where I just use this one of integral the u dv formula as we famously call it. I will just skip through the steps, but we will see what it means. So, Laplace transform of t is simply written as 1 over s square, right. Okay. Similarly, if I have t square or t to the power n, I can just generalize this to an expression like this, that L of t power n is factorial n s power n plus 1. Say if I have to write Laplace transform of t square, that is factorial 2 over s3, that will simply be 2 over s cube, and so on, right. So, this is kind of straightforward to compute. Okay. Let us take sinusoids. What happens to the Laplace transform of sine of a t? Well, I just put it into the formulae, and what I get is the Laplace transform of sine of a t is a over s square plus a square. And okay, we just follow this little computational process here, where I can write sine as something to do sum of some exponential signals. Okay. Similarly, I could even do for cosine signals. The cos Laplace transform of cos of a t is s over s square plus a square. Okay. Now, why are these important, or do these guys come with some beautiful properties? Well, we will investigate them one by one. Sometimes it may happen that I may not be able to compute the Laplace transform just by definition, because I need to solve some complicated integrals, right. So, to simplify this process, we learn certain basic properties of Laplace transform, and these basic properties have been derived again from some basic definitions. And by making use of these basic definitions, the basic definitions plus these properties, we can then go on to get Laplace transforms of more kind of complicated looking signals. Okay. So, let us investigate these properties slowly and one by one. First is the linearity property, right. So, if I take two signals x1 with a Laplace transform x1s, x2 with a Laplace transform x2s, and I define a new signal which is a combination of these two, a times x1 plus b times x2. So, the linearity condition or the linearity property says that the Laplace transform of this signal is simply a, right, with its equivalent Laplace transform plus b with its equivalent Laplace transform. Let us take a very simple example, right. So, I have two signals e power a t as my x1 and say e power b t as my x2, and I want to find Laplace transform of a signal which looks like this, e power a t minus e power b t. Okay. So, what is this? This is simply, according to the property, is Laplace transform of e power a t minus the Laplace transform of e power b t. Okay. And that is simply computed to be 1 over s minus a minus 1 over s minus b. Right. So, I am just individually computing and then adding up. The next property would be the time shifting property, where if I have a signal x t, right, and now I have t shifted by some number t naught. Okay. The Laplace transform under the time shifting thing would just be e power minus s with the shifted amount of time times x of s. Okay. So, this is kind of also straightforward to verify. So, if I have a signal that x of t equal to t, right, which essentially looks like this, and then I have another signal which is, so this x, let me call this x shifted by t minus some number a is t minus a, which is like this. So, the Laplace transform of this guy I know is 1 over x square. Okay. Now, what is the Laplace transform of x t minus a? This would simply be, well, I still have this x of s which is 1 over s square, okay, and in addition I have e power minus s with the amount of time t0 which the signal has shifted. So, this guy a. So, this is e power s times a over 1 over s square. So, this is how it looks like. Okay. So, the third property is the time scaling property, where I have a signal again x of t with an equivalent Laplace transform x of s. I have x of a times t would just be 1 over magnitude of a s x of s over a. Okay. So, let us see this in terms of say a simple sinusoidal signal. Okay. So, from the earlier derived formulas, let us say Laplace transform of sine of t would be 1 over s square plus 1. Okay. Now, if I instead of t, I have to find what is the Laplace transform of sine of a times t, right. The time is scaled with a factor of a, like in one of our examples we had the signal 2 sine 2t, right, in the second slide. Okay. So, what would this be? By this property, this would be 1 over the magnitude of a with the Laplace transform with of the same signal with s replaced by s over a. So, I have this one s over a square plus 1. Okay. Now, I write this down and expand this, and what I have is now this guy would be a over s square plus a square. This is what we had exactly derived earlier. Okay. Now, the next property is time reversal. It's kind of straightforward, right. You just replace the minus t with a minus s. Okay. We will not do any examples on this. Okay. Now, the next important property is that of time differentiation. Okay. So, I have a signal x of t with its equivalent Laplace transform x of s. So, what the property tells me is that dx t of dt, the Laplace transform of this would be s times x of s minus x of 0, where this is initial condition of the signal, and similarly I can even do for higher order derivatives. Okay. So, let us see if we could like do an example with this. So, let us say I have a signal, say I start with sine of t, for which I know that the Laplace transform is 1 over s square plus 1. Okay. Now, Laplace transform of d of dt of sine t with this formula, assume that x of 0 equal to 0 for simplicity, that d of dt of sine t, the Laplace transform of this guy with this property would simply be s times x of s, right. Now, what is x of s? This is 1 over s square plus 1, and therefore, Laplace transform of d of dt of sine of t would be s multiplied by the Laplace transform of the signal itself, and this is again nothing but the Laplace transform of cos of t, as we had verified earlier. Okay. Okay. Similarly to with the time integration, right. So, if I have a signal, I integrate with 0 to t, this is just as replacing it by 1 over s. Okay. You can just do the reverse of this example, and that will be kind of obvious here. Okay. Next would be the frequency differentiation. So, if I take a signal x of t, right, and I multiply it, so x of t has an equivalent Laplace transform of x of s, I multiply this by t, this would amount to just differentiating the Laplace transform of this original signal by s and adding a negative sign. Okay. So, let us say I have to do this Laplace transform of t of some signal sine of a t. Okay. So, this would by this property just be minus d over ds, right, this guy, times the Laplace transform of only this guy, right, x of s, that is a over s square plus a square, and this becomes now a straightforward thing for me to compute, right, then just taking the formula, then multiplying this by e power minus st and so on. Okay. So, this just becomes twice a s over s square plus a square whole square, right. So, this is kind of a very useful property for me, and I can just send this to when I am just multiplying it with t n times. Okay. Similarly, I have the property of frequency integration, that if I have x of t with the equivalent Laplace transform x of s, 1 over t x of t would just be this integral s to infinity x u du. Okay. Frequency shifting, right. So, if I have again a signal x of t with the equivalent Laplace transform x of s, I multiply this signal with e power s naught t, it would just be amount to substituting in the original Laplace transform of the signal s with s minus s naught. Okay. So, let us say I want to do this something like this, Laplace transform of my original signal is sine of a t, and I say I just multiply this to the left by e power a t. Okay. So, this would simply be, okay, what is this? So, the Laplace transform of sine of a t, Okay, what is this? Laplace transform of sine of a t is a over s square plus a square. Now, multiplying this by e power a t would just mean substituting s with s minus s 0. In this case, s 0 is a. Okay. So, this would just be a over s minus a whole square plus a square. Okay. And similarly, if I have periodic function with some period p, the Laplace transform is simply given by this formula. And so, I do not really need to go from 0 to infinity, but I can just make use of the period. I will not derive each of this, we may have learned this in our earlier courses, but I am just doing a bit of a quick recap of these things. Okay. Now, some other important properties. So, first is called the initial value theorem. Right. So, what does the initial value theorem do? It relates again the signals to the in the time domain to the one in the s domain as time approaches 0. So, limit t goes to 0 of x of t would be limit s tends to infinity of s times x of s. Okay. So, let us take this little example. So, the signal x of t goes as 3 plus 4 cos t. If I just do the limit, 3 stays as it is, cos of 0 becomes 1. So, I have a 4 here. So, the limit goes to 7. Okay. So, in the s domain, I just use this formula that limit s tends to infinity s x of s is limit s tends to 0, I multiply with s and then the Laplace transform of x of s. 3 is like a step of size 3, that will be the Laplace transform would be 3 over s and 4 times cos t, and we in our earlier slides had computed the Laplace transform for cos of t. So, I just do all the computations, take the limit and I come back to this number 7. Okay. So, only thing which we need to be careful here is that the Laplace transform should exist. I will give you a counter example of this shortly. Similarly, with the final value theorem, what happens to my signal as time goes to infinity? So, the final value theorem says that limit t going to infinity x of t is equivalent to limit s going to 0 s times x of s. Okay. So, let us take an example. So, I have this example x of t is 1 minus e power minus 2 t by 2. I do the simple computations and I get that the final value that this signal converges to 1 over 2 as e power minus t goes to infinity as t goes to infinity. So, this term will just disappear. Okay. So, how does it look in the Laplacian domain? Well, 1 becomes 1 over s, e power minus 2 t becomes 1 over s plus 2, I apply the limits and I get 1 over s plus 2. Again, we have to make sure that the limit actually exists. Okay. So, let us do something very quickly of a case when the limit may not exist all the time. Okay. Let us take the case of a signal 1 over s minus 3 and I say I just blindly apply this final value theorem that limit s going to 0 s times this would give me a value of minus 1 over 3. Okay. Now, is this correct? So, let me also do the time domain analysis like I do over here. So, this signal can be written as 1 over s minus 1 over s minus 3. So, you have a s minus 3 and this going away and a minus 1 over 3 here. And if I write down the equivalent time domain representation of this, so what I will have here is 1 over 3 and 1 over s corresponds to 1 in the time domain, like the Laplace transform of 1 is 1 over s minus e power 3 t. Okay. Now, if I take the limit of this signal as t going to infinity, I see that this term actually blows up, right. The limit does not exist. And therefore, I just do not blindly apply, I should make sure that first the limit actually exists. So, this final value theorem and also the initial value theorem is applicable only in the cases where Laplace transform exists and its limit exists as s tends to 0, and also the final value should exist. That is what we should be careful of when we apply the final value theorem. Okay, so what we have done so far is had a quick recap of Laplace transforms, basic properties, and how we use those properties to compute Laplace transform of some little complicated looking signals, and then the initial value theorem, the final value theorem, and what we should be careful of while applying those theorems. Next we will discuss the inverse Laplace transform. So, if I can go from the time domain to the S domain, can I actually come back? And another important property called the convolution, which will be very important for us in the control setting. Okay, thanks for your attention.